Good afternoon, everyone. I'm Peter Gillard from Frazer-Nash Consultancy. Thank you for joining this IMechE webinar on developing the UK nuclear fusion industry. This is the second of a two-part webinar. Part one, last week, gave a view from the UK public sector. Part two, today, gives a private sector view. Today's webinar is being presented by Nick Walkden, lead fusion consultant at Frazer-Nash. Nick has worked in both the public and private sides of the fusion sector over a 13-year career. He's an award-winning plasma physicist, having led experimental teams on all of Europe's major tokamak devices. He spent much of the last 4 years supporting the development of national fusion policy and strategy in the UK. In July, Nick was appointed as UK Director of the Fusion Industry Association. Nick's going to talk for 35 to 40 minutes, and we'll then have 20 minutes or so to take questions. Please type any questions you have into the Ask Questions tab in the webinar window. You can do that whilst Nick is talking and also during the Q&A itself. Nick, thanks for agreeing to talk to us today. Over to you.
Thank you very much, Pete. Thanks for the nice introduction there. Yes, hello everybody. It's great to be delivering this webinar to you today. So as Pete says, I kind of wear two hats at the moment. I am the lead fusion consultant at Frazer-Nash Consultancy. And I always like to say to people I know quite a lot about fusion and very little about anything else. So this is right in my sweet spot today. I'm also if I can make my screen move, I'm also the UK Director of the Fusion Industry Association. And in the Fusion Industry Association is the unified voice of the fusion private sector. And we work with governments, labs, partners, industry, all around the world, all with the aim of making fusion happen and making it happen on accelerated timelines that can hit climate change hard. So this is kind of the first talk I've really given where I've worn those dual hats. So this is really exciting for me. But let's start off with why should you care about fusion? Why should anyone care about fusion? Why do I care so much about it? Populations are growing. In all projections, populations around the world grow to more than 8 billion people, 9 billion people towards the middle of this century, with really aggressive policy on education, particularly female education in third world countries. That population growth starts to turn over towards the end of this century, but never really significantly below where we're at now. But in many scenarios, and probably depressingly what we would consider more likely scenarios, that turnover doesn't happen. And so we're looking at possible futures where the world doubles in population compared to where we are now. Now, at the same time, the social well-being of humans is really strongly linked to energy use. So how much electricity does each person have available to them is really strongly linked to how well people live. If you've never come across it before, this is called the Human Development Index, and it takes a whole load of different measures and combines it into one quantum, which gives you an indication of where, I guess, standard of living and standard of and social standard is with one metric. And you can see that in developed nations in the red, we tend to be very high up in HDI. We have a very high standard of living. We're very fortunate. And that corresponds really strongly with increased electricity availability per capita. It turns out that this curve starts to turn over around about 4,000 kilowatt hours per person. So we, especially in developed countries, have an absolute moral imperative to create a global society where we can bring everybody up this curve. And if we want to increase standard of living, one of the most brute force ways of doing that is to provide the capacity to give everybody 4,000 kilowatt hours per capita of electricity. Now, of course, that is going to drive more emissions because we have more energy coming from sources that produce emissions. It's going to drive more emissions. So, and that at the crux of it is what really the climate issue is how do we deliver the energy we need for a morally sound society, a society where everyone can thrive, but we do not put harmful emittents into the atmosphere. We don't ruin the ecology of the world. We don't change biodiversity. We don't change sea currents, add to ocean acidification. Even if we are successful in getting to a net zero 2050 target, this is what net zero 2050 looks like, by the way. This is the International Energy Agency's roadmap, and this scenario achieves net zero in 2050. Even in net zero 2050, we still have the equivalent of 3.5 billion tons of oil in our energy system using fossil fuels. So this is like the very best case scenario where, by the way, governments today have to massively ramp up investment and policy action to get there. Even in that situation, we still have 3.5 billion tons of oil equivalent. Now, I've just told you that it's very likely populations will be continuing to grow after this point. This is not a long-term sustainable solution. This is an essential part of a long-term sustainable solution, but it is not a long-term sustainable solution. Now, the problem, of course, with this picture is where do you go? If this isn't a long-term sustainable solution, where do you go? Because we've already tried to get almost everything we can in the mix there. Where do you go from there? Now, if numbers aren't emotive enough for you, the reason really that I do what I do and I care is this. This is my son. He's called Artie. This is when he was a cute baby. He's now an absolute snotty toddler, but I love him dearly. He will be 30 in 2050. So let's think about that for a sec. Artie will spend the majority of his life in the post-2050 era. He'll be 80 by 2100. So I very, very much hope that he lives to see the turn of the next century. This is why we do what we do. This is why we should all care about this, because we need to today create the solutions that provide long-term sustainability for our future generations. And that is fundamentally why we should all care about fusion. But what is fusion? So fusion, I assume that everyone on the call knows when I say fusion, what I'm really talking about is two atomic nuclei coming together, fusing, binding, and creating new products from that reaction. When they do that, of course, the energy mass equivalence kicks in, and we get more energy. We get lower masses of the products than we do the reactants, and therefore we get energy out. But what fusion is really is a breakthrough energy source. It's clean, does not produce carbon in the process that you're creating energy with. Of course, you'll have embedded carbon in the plant that you're creating, especially in first generations before we've decarbonized industry. But it's a clean process. It's dispatchable, so you can produce reliable, non-variable electricity using fusion. It's safe. There is no meltdown scenario in fusion. There's no long-lived radioactive waste, no fissile material that get produced in the fusion reaction. It's abundant. So the fuel sources that you really need for fusion are deuterium, which exists in seawater, and lithium, which, of course, we know that there's a critical mineral shortage for lithium, but the requirement for fusion is much less per kilowatt hour than energy storage or other sources. So we have an abundant fuel source. We think it can be competitive on economics. We think it can be either at least competitive, if not favorable, to other energy sources. And it's not just electricity we can care about, or we can address with fusion. We can look at hydrogen, we can look at district heating, industrial heating, desalination, propulsion of spacecrafts. It's very very flexible. It's also a solution to long-term sustainability, because it can address clean, sustainable baseload power. Or at least I think the primary competitor here is coal and gas carbon capture, actually. So not only can we add more baseload electricity to the grid, but we can start taking carbon out of the atmosphere without having to burn more of it. So that's a huge advantage of fusion. It's a complement to renewables. It's not going to replace renewables. We don't think it should. But for a renewable electricity grid, you need a reliable baseload supply. and fusion can provide that. And it's widely adaptable to other applications, much like SMRs and AMRs in the nuclear sector, for example. Electricity is only 20% of primary energy today, likely to move up to about 50% as electrification of different industrial sectors happens over the next 30 years or so. But it's not all of primary energy, and fusion produces a lot of heat. It does a really good job of producing heat. So if we can harness that heat and use it for other kinds of energy sources as well, that adds more to the energy mix. Just one moment. Okay. Fusion is also an absolutely unparalleled business opportunity. Bloomberg have estimated that it could have a market cap up to $40 trillion when fusion comes to the energy markets. McKinsey have done a deep dive into fusion and believe that it could be the dominant source of clean energy in the European grids as of 2050. And fusion has all the potential to break the geopolitics of energy. So energy security and dependence on dictators or other nations with nefarious intentions becomes a thing of the past if we can deploy fusion technologies. So finally, fusion is an engineering and materials and a manufacturing marketplace. The fuels for fusion are abundant. So fuel, it will not be a fuel and resource economy like the oil and gas industry, and to some extent the nuclear fission industry. It does not produce any fissile products. So regulations can be very different to nuclear regulations, and the industry will not be as beholden to regulation in the way it's set up as the nuclear industry is. And it's baseload power using very conventional energy conversion engineering, so it doesn't require modification for grid infrastructure. So if it doesn't need these things, it looks very different in an economic sense to any kind of energy production that we have today. So what does fusion need? Fusion needs science and engineering. It's very, very complex. A lot of the elements in fusion are extremely complex, right at the cutting frontier edge of science and engineering. So science and engineering knowledge and know-how become extremely valuable commodities in the fusion marketplace. It's a manufacturing problem fundamentally. If you can design and engineer and then build all of the components you need for a fusion power plant, fuel isn't really an issue. So you can then create fusion energy. So fusion is a manufacturing marketplace, and it's a materials marketplace because the kind of conditions that we're going to have in fusion power plants are so extreme and different to many of the other conditions we have on Earth today. It becomes a marketplace for new and advanced. Could someone just confirm I'm still sharing my screen? Have I?
No, it has stopped.
Sorry about that. I'm not quite sure what happened there. There we go. Apologies for that. So yes, fusion becomes a marketplace for new and tailored materials at scale. So if you have the knowledge and know-how, if you have the manufacturing capacity and the ability to create and scale new materials, you can do fusion. Why? But I really want to give you the message that fusion is in a really unique moment in history at the moment. And everybody has been saying that for 20 years or however long, but it's really true now, and I'll tell you why. First off, we have scientific proof from the National Ignition Facility in the US that fusion works. Last year, they proved that you could get 1.5 times the energy out of this capsule, out of this entire fuel target, than the amount of energy that's put into it. So that's more energy out than put in. Now, that's very, very far from net energy producing, because these lasers require an awful lot of energy to put into this target, but they were never ever designed to be net energy producing. The point is, if you could make much more efficient lasers to put that energy into this target, then you know that you're going to get a net gain out. And that's scientific proof. That is incontrovertible proof. At the same time, we have long-term commitments to supply fusion energy starting to emerge. So in the public sector, we heard last week about the STEP programme. The UK government are very soon going to be launching procurements for the very, very first contracts ever let by a government to build a fusion pilot plant. And I actually think that's been understated. That's a really, really significant thing. The first time that's ever happened in the world. And in the private sector, we see agreements now starting to pop up. Like Helion Energy have just signed an agreement with Nucor to provide 500 megawatt electric of fusion power to one of their future production plants. So we're starting to see now long-term commitments to provide fusion energy emerge. And at the same time, we have historic levels of funding entering the sector. We have had more private investment into the fusion sector in the last 2 years than the entirety of its history. So if you want some proof that any sector, fusion or any sector, is ready to commercialize, you want scientific proof, you want long-term commitment, and you want money. And those three things are now happening in fusion. So it's a really, really exciting and unique time in fusion development. At the same time, we've got modern scientific and technological advances now coming and breaking through that make a real difference to fusion. So AI and exascale computing, we can now solve models, run simulations, do digital design that we could never do before, that allow us to get to a level of complexity and understanding that we could never have even 5 years ago. Advanced manufacturing techniques mean that we can make components that are much, much more complex now than we ever could before and can meet the challenges that fusion throws at them. And likewise, new materials, advanced steels, composites, coatings, new materials are becoming available which can start to withstand some of the environment and harsh challenges that fusion can throw at them. Advanced plasma science, of course, has always been essential at driving development in fusion. The more we can understand what's going on in the center of our fusion devices, the better. And fundamentally, new business models are starting to emerge, new ways of funding, new ways of developing innovations in the private sector are emerging, which allows us to start to develop fusion at scale. And we sit on a basis of a fusion development that is really quite successful. So this graph is quite technical. All you really need to know is that the y-axis is a metric for fusion performance. And you can see that over the last decades, our ability to create machines that can perform well in fusion has gone through several orders of magnitude. We're now at the stage where we start to see fusion gains. So we start to see more energy out than put in. And devices that are planned in the world now are really planned in this quadrant where they're being planned for this kind of operating space to start producing demonstrators that you can get net energy gain out of fusion. And that's really, really exciting. So in this context, what does the private sector do? We heard about how the public sector in the UK is moving forwards. What does the private sector do? The Fusion Industry Association, the way that we see the sector, we see the fusion private sector as being formed by the primary developers, the companies that are formed to pursue novel fusion technologies, and the ecosystem, the supply chain, the NGOs, the academic ecosystem around them that supports that development. That's how we view the private sector. And this is not exhaustive, by the way. This is a list of some of the fusion companies that are in existence today and that are doing really, really well today to develop some of these concepts for novel fusion technologies. All of these are members of the Fusion Industry Association. So it's a really, really exciting landscape, loads and loads of diversity. And it's very, very spread geographically. So the bulk of fusion companies are in the US because the US has the national lab infrastructure, the scale and the funding opportunities there to really stimulate a lot of this spin out. But there's also a large number of companies that are not in the US. The UK has 3 companies headquartered, several more with stakes in the UK, Germany, similarly with 3 companies, and Japan, and then several companies around the world that are all pursuing different technologies, and all of them with supply chains and ecosystems around them to support that development. And when I talk about the ecosystem, I mean this. Again, this is not by any means exhaustive, but there are many, many, many companies now around the world that either part or all of their operation is now dedicated to supporting the development of fusion. Big names like Google, oil and gas companies like Eni, right down to really innovative small companies like Woodruff Scientific, Oxford Sigma, who have fusion as their core focus in the work that they deliver into as a supplier. And this has really emerged very recently. So historically, there was an awful lot of fusion research into lots of different technology concepts in the 60s, 70s, and 80s. And because of the pressures of public sector funding and the need to manage taxpayer money effectively, and pursue, I guess, projects where there's clear headwind, this diversity really got funneled into, largely speaking, two pursuits, the tokamak, and most public sector fusion research today is in this tokamak concept, and laser inertial fusion, where you're using lasers to compress fuel targets, which of course is also heavily funded by defense funding. However, with that narrowing down of concepts in the public sector comes a rediversification of concepts in the private sector, enabled by a lot of those technological advancements that I spoke about before. So if we when we last surveyed the private sector earlier this year, there are now more than 25 distinct technological approaches being pursued by private sector companies in fusion. And we think that's really exciting. That's a really, really exciting place for the landscape to be in, where you've got the private sector that can move fast, can take risk, can rapidly innovate, looking at this diversification of technologies. And you've got the public sector, which sits on the back of years and years and years of scientific efforts, pursuing the routes where they have the strongest capability to do so. So we think that's a really healthy place for the sector to be in. And there's a lot of ambition, there's a lot of confidence within the private sector. So when surveyed, 26 of 40 respondents said that they believe the first fusion power plant will deliver electricity to the grid by 2035, and the majority believe that it's by 2040. So that's a resounding air of confidence that fusion is not, or fusion is on the way, with ambitions to deliver electricity to the grid in the 2030s. And this is, if you try and take a canonical timeline for fusion from the private sector, this is broadly speaking what it looks like. Now, every company will have its own roadmap. Some are more aggressive than this, some are more relaxed than this, some will skip out some of these stages, others will pursue in a very, very stepwise fashion. But broadly speaking, we sit on the back of 60 years plus of scientific research in the public sector, looking at proving out different concepts, a variety of different technological concepts, through private sector cash and through private sector investment in the mid-2020s. And we see many companies now in this phase, looking to design, build, commission pilot plants and demonstrator plants in the late 2020s and early 2030s, and looking to operate them and get towards first energy sales or first products licensing in the early 2030s, such that we have rollout of commercial fusion mid-2030s and onwards, up to global deployment. And what's driving this? Fundamentally, the thing that is driving this timeline is the imperative to have an impact, the imperative to do something on a timescale that can impact on long-term sustainability. That's why we drive this timescale, and that's why it's so fundamental that the pace of acceleration is maintained in the private sector. And investment is in a good place. So as I said, there's now more than $6 billion of private capital invested in fusion to date. The majority of this, more than $4 billion in the last 2 years. And the majority of this investment through private sector capital, through venture funds, through other sources of private sector capital. Just in the last year, we've seen a real diversity of different funding raises in the fusion sector, from sort of seed round capital like Fear Energy, NT Tau, General, and a few others here, raising those early stage rounds so that they can do the scientific development and scientific demonstration, to later series raises like that by TAE Technologies, looking at funding the building and development of demonstrator class devices, the devices that are going to prove and demonstrate fusion energy production. And it's not just about money, right? Fusion is creating jobs. So just last year, we surveyed 975 new jobs created in fusion companies, 3,000 created in the supply chain, just based off these fusion companies and the investment that they've raised. And this will grow. This will grow exponentially as the sector moves towards demonstration and demonstrator and pilot plant class devices. And that money does not sit in these companies. It doesn't just stay in bank accounts. It doesn't just fund scientific research. Last year alone, more than $500 million was spent in the supply chain on specialized components, materials, engineering, all sorts. And the supply chain is ready to answer that challenge. When surveyed, suppliers absolutely categorically are prepared and are ready to scale up. They are ready to scale up with fusion developers to deploy their plants, deliver their programs, either at risk or fully ready to invest in their own capacity to meet that future demand. So we're in a really, really good place where investment continues and the supply chain and enabling ecosystem is ready to scale. There are now more than 40 companies developing fusion technologies, and they've really exploded in the last 5 years. And this is largely down to the availability of very, very effective funding mechanisms in the US and elsewhere, stimulating spin-outs from universities, from public labs, from inventors and innovators into fusion companies to pursue a really wide technological diversity. In the UK, we have 7. So we have 2 or 3 companies headquartered in the UK. That's First Light Fusion, Tokamak Energy, and Crossfield Fusion, and several other companies who have significant stakes in the UK ecosystem. And I thought it'd be great just to give you a quick introduction to the 2 largest companies headquartered in the UK. That's First Light Fusion and Tokamak Energy. First Light Fusion are based over in Yarnton in Oxfordshire, founded in 2011 as a spin-out from the University of Oxford and Imperial College. They've raised nearly $100 million to date, and they employ over more than 95, I think probably more than 100 employees now, seeking to deliver their pilot plants on the sort of 2030s, early 2030s timescale. Now, their concept is really interesting because in traditional inertial fusion, as we call it, you keep some kind of fuel capsule suspended and you fire lasers at that capsule to compress it, super compress it, heat it, and do fusion. Now that requires you to be able to compress it symmetrically all around the target. So you have to fire lasers from all different angles in order to symmetrically compress this target. First Light Fusion take a different approach. Instead, they have developed really innovative configurations of targets, which when hit from one side, can convert a shockwave that is initially a planar shockwave into a spherical shockwave within the target, and that causes the fuel capsule to compress. So really, really innovative approach to this inertial fusion problem. They're the only company in the world pursuing this approach, and you can see a couple of different facilities that they've got at the Yarnton outfit in order to investigate this approach and develop it forwards. And they have a pilot plant to design. So you can see here you would be injecting some kind of projectile down, which would hit a fuel capsule in this space here, cause fusion with all of the nasty reactants and heat being caught in a curtain of liquid metal. And they're doing very well indeed. They've demonstrated fusion on their, yes, here. So they've demonstrated fusion already in one of their targets, albeit at a low level, but in line with predictions, and are now working with partners at the UKA and in the supply chain to develop towards their demonstrator device, which is called M4. So this is M4. M4 will be the world's most powerful pulse power device. It will be more powerful than any other pulse power device that we have in the world at the moment, with many, many, many capacitor banks sitting around the edge, all discharging all of their power in a very, very short pulse that converges right at this point in the center to launch a plate up and hit their fuel. And the point of this device is to demonstrate fusion gain. So very, very exciting device in the plans. Tokamak Energy are focused on tokamaks. So we've had an example of an inertial fusion company. Now we have an example of a company pursuing a tokamak in the private sector. And fundamentally, their approach focuses on two innovations: high temperature superconductors and something called a spherical tokamak, which we heard about last week. They've raised nearly $250 million and have about 250 employees and have been going since 2009, again in Oxfordshire, in Milton Park in Didcot. And yes, so their technology combines two innovations. First is the spherical tokamak. So this is, you take something that looks like a donut and you compress it all down near the center. It turns out that is a much, much more efficient way of confining the energy inside your fusion device. And so you can more efficiently run the system, allowing you to get more energy out in a smaller device at lower cost. Now, combine that idea with high temperature superconductors. So HTS coils allow you to get to very, very high magnetic fields. And all of a sudden, you end up with a very, very viable device concept for getting very efficient fusion energy. They have built several devices like First Light Fusion. ST40 was a spherical tokamak that they built, constructed, and operated in 2017, and is the highest magnetic field spherical tokamak ever constructed. And went on to achieve 100 million degrees in spherical tokamak plasmas last year, an absolute landmark in the sector. And aside from that, they're also developing their superconducting coil technology. So they've demonstrated 26.2 Teslas of magnetic field in collaboration with CERN. And similarly, Tokamak Energy are a very international program. So they're headquartered in the UK, but they work with partners all across the world. They've recently been selected as part of a milestone program in the US, and they work with really major partners and governments all across the world, pursuing fundamentally two next stage devices. The first is called Demo 4, and this is basically saying what happens if you put all of the magnets that you're going to need in your device in the right configuration and turn them on. What are the engineering stresses? What are the limitations in this, the engineering limitations in this configuration? And do that ahead of building the full device so that you know how to engineer all of these magnetic coils and their support structures ahead of time. And at the same time, develop and work towards a next stage device which utilizes the power of HTS magnets to again achieve fusion gain conditions. So again, a demonstrator class device. And that's not all. So those companies are headquartered in the UK, but international fusion developers are becoming are very aware of what's happening in the UK because of the strong policy, the strong ecosystem that we have in place here, and are looking to take advantage of that and collaborate and develop their programs here. I highlight that there are many. I highlight two here because these are the two companies in the world that have raised more than $1 billion in investment to develop their programs. Commonwealth Fusion Systems have raised $2 billion. TAE Technologies have raised just over $1 billion. And both of them are now working in the UK collaboratively with partners in the UK, and even have parts of their operations in the UK because of the ecosystem that we have in place. We also have a really vibrant landscape of companies developing enabling technologies and other aspects within the supply chain. I highlight four here. Kyoto Fusioneering are really world leaders in elements of the fusion fuel cycle, the fusion power cycle, and a lot of the technologies that will be absolutely essential for fusion to come to the grid. Oxford Sigma, leading lights in the world of fusion materials with really, really interesting new innovative capabilities in developing materials and data sets to support that. Fusion Energy Insights are a company that really focus on information and bringing information into the hands of those who don't have it but need it to help move fusion forwards, like investors, business communities, others. And Digilab are a really great example of innovative digital engineering using AI, uncertainty quantification, and machine learning to move fusion science and engineering forwards. And fusion is a major part of their operation as well. I would be remiss if I didn't talk about my own company, Frazer-Nash Consultancy. And I use this more here as a kind of example that the supply chain companies do not just deliver, individual things into fusion, but they are fundamental to the development of fusion programs. In Frazer-Nash, we've done many, many projects in different areas of fusion design, both at a component level, but also at full reactor-wide level of design and analysis. I'm not going to go through all of these, but this is to show you that in fusion, the supply chain and the enabling companies play a really, really pivotal role in the development of these concepts. And fusion is a global affair. Geopolitics is becoming important and prominent in fusion. And actually, the UK has driven a lot of that by publishing the world's first national fusion strategy. But this has been echoed elsewhere. So the US has a very aggressive policy around fusion. They funded a recent milestone program to follow the kind of examples that SpaceX have set in how you develop innovations to scale. Japan have recently published a fusion strategy, which again is aggressive and really focuses on building industrial capability. The EU have a strong fusion program built on a really, really strong historic legacy of public sector research. And China have a very ambitious program to build right up to a test reactor in the 2030s. And of course, when China choose to do something, they choose to do it big. So what elements do we need to create a really successful fusion industry here in the UK? Well, at the FIA, we think there are fundamentally three things needed to build a really successful fusion industry. The first is to have really effective public-private partnerships. Fusion is hard. Fusion will always be hard, and we cannot just rely on the innovation capacity of the private sector. We cannot just rely on the scientific legacy of the public sector. We need public-private partnerships that have long-term commitment, that effectively share and balance risk and costs between them, and that can deploy the legacy of scientific research in the public sector effectively with the innovation and acceleration capacity of the private sector. We need regulatory certainty, right? Fusion is a very, very different problem to the nuclear industries, to any other industry that the world has ever seen before, and deserves a bespoke regulatory framework that meets its needs and respects that difference. And we need both development and certainty around that approach. And at the point that fusion comes to the market, we would like fusion should have fair and equal access to incentives, tax breaks, other types of incentives that any other clean energy technology has now. We don't expect that to be important right now, or we don't expect that to be something that will be claimed at the moment, but we need government to start to indicate that will be the case to provide some certainty. Because of course this is all a step ladder, right? You have companies, startups forming down here, doing innovative things, validating their ideas, scaling up the staircase, demonstrating that their concept works, deploying sort of $500 million to demonstrate that concept, right up to full deployable commercialization at the top of this staircase. When you're sitting at the bottom of this staircase, you do not have much money to put into things. So you need grants, you need seed capital, you need kind of almost no strings attached ability to fund your research, look at your innovation, fail fast or succeed fast. You need research collaborations that are effective, that are enabling to your program, that take the science and the engineering being done in the public sector and really effectively use that to validate your own concepts and develop your own concepts. And you need access. You need access to public sector research, expertise, and facilities that taxpayer money has funded for the last several decades. We need access for public sector institutes to build off of these. As you're scaling up your program, you need to start looking at much larger financing, much larger capital raises. And the public sector has a big role to play there by looking at innovative ways of sharing that cost burden. Governments all around the world want to develop fusion. They want fusion to come to the grid. The private sector is very well placed to take a lot of that risk, to own the risk of fusion development at reasonable and appropriate cost share arrangements with public sector programs. And we see that start to happen, happening really effectively now in the US. We need partnerships, long-term partnerships with national labs where they have facilities and capabilities that it is in no one's interest for private sector companies to be developing. And we need regulation that is innovation friendly, that allows you to have some certainty about what will be required of you, but also with the freedom to innovate along that journey, and permitting that is effective, but also enabling. And finally, when we get to the point of deployment, we need a level playing field with other clean technologies, with other green technologies. But importantly, we need that signal now. We need to know from governments, from buyers now, that we will have that level playing field, that incentives will be applied equally to fusion as they are in renewables, in other clean technologies. And in my view, we need governments to start committing to not just develop fusion technology, but to buy fusion energy when it becomes available. There are lots of different financing options for how to do that, and we think government should start moving towards how should a government buy fusion energy. In the UK, it could be a contract for difference, for example. So let's look forward. What does a world-leading fusion industry in the UK look like with global export potential? We think it looks like industry. The industry, I say industry twice there. The sort of private sector actors in that, building multiple pilot plants with different sizes, different technologies, a real diversity of approach. Many shots on goal. The more shots on goal we have, the more likely one is to hit the target. We need government to be creating the infrastructure and the ecosystem that enable this to happen, enable the commercialization of these technologies, which includes advanced scientific computational and test facilities. It includes regulation, and it includes financing. And we need national laboratories and universities to focus on creating the workforce that will deliver all of this and will run these future fusion facilities. It's absolutely essential that we have the right people in the right places at the right times to do all of these things. And all of this should work absolutely in concert and should come together under national strategies agreed between all of these different players. So that's my last slide. That's my kind of vision for you of what I think a world-leading fusion industry would look like. I will just say, as I know there are many people from many different companies on the call, if you want to know more, if you're interested to know more, the Fusion Industry Association is a membership organization. If you are building fusion technologies and you want to join, you can look at full membership. If you're in the ecosystem, you can look at affiliate membership. Just please reach out to me if you're at all interested in joining. It's a really, really great community. You can help steer the policy that we're putting to governments, and you can come to networking events, meet businesses that you might want to work with and forge partnerships with, and just be part of what is probably the most important technology development movement in the world at the moment. So on that, thank you very much. Like I say, I'm wearing two hats today, so I'll give you two emails to contact me with. But I'll leave it there and open up to questions.
Nick, thank you. That was fantastic. Really interesting. Absolutely fascinating to see what's going on in fusion. Thank you. We've got some questions, but we're going to have time for more. So if that's prompted any questions, please type those into the box. There'll be plenty of time for Nick to get to those. So we'll start with the ones we have. So we've got a question about magnets and rare earths. So with the hunt on for rare earths and the demand from other areas, which rare earths would need to be supplied for the magnets?
Oh, that's a good and very detailed question. What a way
Yeah,
to
I was
start.
wondering if that was in your area of expertise.
Yeah. Well, yeah. So the HTS technology that's being most actively developed at the moment is REBCO. So any of the rare earths that go into REBCO magnets, they're the ones that that we'll need to focus on. And it's not just rare earths going into the raw material for those magnets, but also the manufacturing capacity to turn those into either wires, tapes of magnets, and then the manufacturing capacity to take those wires and tapes and turn them into the complex structures that we need the magnets to be. So there is a whole supply chain that is forming now around the ability to deliver HTS magnets. This isn't a future thing though. We already, these are already being produced, these HTS REBCO magnets. Look up at some of the work that Commonwealth Fusion Systems are doing, producing big magnets, Tokamak Energy and others. What's nice about fusion is that fusion is driving the development of, being able to build HTS magnets at this kind of scale. And it's not just magnets as well, where we have, critical minerals. Like I said, lithium is a very, very important material for fusion. Very happy to talk much more about the lithium challenge if anyone's interested, but that's a very important material for fusion, not at the scale that you find is needed in like the EV markets or other markets, but but with complexities and sort of requirements on its purification, its enrichment, and other things that differ from technology to technology. And then there are various other metals as well that could or could not be critical, and are not critical depending on the design. Vanadium is talked about. Palladium is a very critical material in separating isotopes of hydrogen. So yeah, there's a real spectrum of materials challenges around fusion, and we're starting to get to the point now where developing those supply chains become a critical path activity for fusion development. Hopefully that answers the question. I've kind of skirted around some of the detail because I'm not an HTS expert, but yeah, look up Rebco magnets if you want to understand a bit more about what kind of materials go into those. Go into those magnets.
Okay, great. Thanks, Nick. So we have a question. What's the estimated energy capacity of a fusion plant? How many sites do you think the UK will be looking to develop in the future?
Oh, that's a great question. It really varies. It really varies. Right. One of the nice, I think nice is actually a disservice to it. One of the essential properties of the fusion industry at the moment is that it has this technological diversity to it. I really at the core of my soul fundamentally believe that if only one fusion concept ever builds a pilot plant and deploys, fusion will fail to have an impact, because it will take so long to innovate on that concept and build the second and third generations that I just think it will be too hard for fusion to have a concept. And that's a personal view. This is not a Frazer-Nash view. This is not an FIA view. That is a personal view. So I think the diversity that we have in the fusion industry is really important. Now, with that diversity comes a whole range of different target markets, right? Many of the companies are targeting electricity and baseload electricity as their primary market, and so that means plants that are looking towards sort of a few hundred to a few thousand megawatts electric capacity production. So in the UK, well, that's kind of a hard question to say. How many sites do you think the UK would be looking to develop? I would say, well, yeah, that's a really hard question to answer, because I don't, to be honest, if I'm really brutally honest, the UK probably is fine, right? The UK, we will probably be fine for net zero using offshore wind, others, current nuclear capacity. But fusion and net zero is not a UK centered problem, it's a global problem. I think we should be aiming for at least 10% of production capacity by fusion. So that's 1 terawatt electric. So that's probably 1,000 gigawatt electric fusion plants. That's the kind of scale that I think we should all be looking to deliver through fusion.
Okay, great. Thanks, Nick. So sort of broadly the capacity of a traditional coal station or a CCG gas station, or
yeah, exactly. I think it varies, right? So for baseload electricity, yeah, you're looking at that sort of capacity. So a few hundred megawatt electric up to a few gigawatt electric, but also lots of the concepts that are being pursued, particularly the smaller ones, are very good at sort of micro reactor level. So 10 megawatt, 20, 30 megawatts of power. They are the ones that may be more better utilized in hydrogen production, ammonia production, desalination plants, industrial heating, those kind of applications as well.
Okay, great. Thanks, Nick. What is the longest nuclear fusion reaction so far? And are the nuclear reactor materials sustainable in the long term?
That's a great question. Yeah, so that's kind of two questions. So I don't know the exact numbers off the top of my head, but the longest a fusion reaction has been sustained for is a few thousand seconds, I believe. To be honest, I can't remember. But also it's worth saying here that length of time is not necessarily the right metric, because different, some concepts are fundamentally pulsed. So whilst the NIF result, for example, only happened over a nanosecond or a few hundred nanoseconds, it produced fusion gain over whatever kind of time frame you're looking at between that and the next laser fire. And one of the things that's really stopping modern day devices from running longer than that do want to do steady state is just not having the magnet technology available. So with the advent of, or the invent of HTS technology, we expect the next set of devices to be able to operate for much, much longer times. Some of them towards steady state. So some companies in that are pursuing certain technologies are looking at hours or longer, 24 hours for their demonstrator class devices. Are the nuclear materials sustainable in long term is a very different question, and that's a very good question, because the neutron environment is a very, very harsh environment for materials, and it's an area of really active development in the community. So there is a lot of development around radiation resistant materials, radiation tolerant steels, ODS steels, RAFM steels, Eurofur, that can handle that environment, or utilizing much more forgiving materials like liquid metals and things like that can essentially self-repair. So there isn't really an easy answer to that. Are the nuclear materials sustainable in the long term? That is an area of active development, and it's an area that's a challenge at different levels, but it's a challenge for everyone in the field. And it's one of the areas that really public-private partnerships are absolutely the right way to pursue, because there's very little incentive for any one company to try and solve this problem in isolation. This is an area where really strong collaboration between industry, public sector, and private sector is really absolutely essential to getting to the bottom of.
Brilliant. Thanks, Nick. Okay, so another question. What would you say is currently the biggest issue facing the fusion industry? Is it the engineering side, the engineering problems, or is it business and politics side?
Okay. So I didn't put it in the slides. So have a look at the FIA's last annual report, because there are two, right? The science of fusion is really hard, and particularly, not particularly. It's all really hard. There are lots and lots of different challenges, technical challenges with fusion. Probably underlying all of them is provably demonstrating the plasma physics at the core of the device, that you can get, what you need to get hot enough and sustained for long enough to produce heat out. But there are other technical challenges as well, like ranging from materials we've talked about. How do you manufacture the kind of components that you're going to need, very, very complex components, to how are you going to maintain a device that's operational without having our soft, squishy biological human bodies in the way, using robots and stuff like that. So all of that's a problem. Obviously proving, getting the plasmas right at the center to do fusion gain is fundamental to all of that. But actually, within the industry, and rated in this survey by the industry, equivalent in terms of scale of challenge to that is raising the money, right? The fusion pilot plants are not going to be cheap, and fusion, unlike any other energy source developed to date, you will only get to the point where if you've got that payoff after you've built the thing and proven that you can get fusion at scale, because fusion power scales with size in most concepts. So you have to build something big to prove that it can happen. So that requires a huge amount of capital, comparative to technologies where you can prove energy at a lab scale. And it's true for every fusion concept, because the complexity is so high, the technology is so innovative. So I think the answer actually to your question is both. I think getting plasmas to fusion gain conditions is always going to be fundamental to fusion, but actually I think finding ways that we can leverage the power of governments and the scale of private capital with long enough commitment and a high enough risk appetite that we can actually fund these things, I think that is a huge challenge, and one that needs to be addressed. It probably will need new financing routes. It will probably need new and innovative funds being set up to do this. And I think we're only at the tip of that iceberg. And like I said before, I fundamentally believe that we need to have more than just one technology coming to the grid. I really feel that deep in my bones. And that means that we have to have several technologies that are going to be able to raise billions to get to that pilot plant device. So yeah, that's a real challenge, but the payoff matches it, right? The payoff is enormous. The people who come to market first in fusion are going to have one of the most significant market caps in history. So the payoff is enormous, but being able to, raising money is hard, right? Anyone who's ever been in any job where you have to raise money, raising money is hard. And at this scale, it's very, very hard. And it takes a really coordinated business and policy approach.
Okay, great. Thanks, Nick. I think we've probably got time for 2 more questions before we pull this to a close. So I have a question. With China throwing the kitchen sink at fusion, should we not be trying to accelerate our engineering capability so as to not become beholden to one country or group of countries cornering supply and the essential materials and possibly patented concepts?
Yeah, absolutely. And I think that's happening. So fusion has always been and will always be a very international operation, just because the complexity is so high. The sector is where it is because of international cooperation and collaborations across borders. But at the same time, like I said in my slides, we're starting to see geopolitics become much more prevalent now than it ever has been before. Nations that are naturally friendly, the US, the UK, Europe, we're likely to see those relationships continue and in fusion be very, very strong, and we hope that that's the case. But absolutely, we should match the enthusiasm shown by other areas of the world in getting to fusion with our own, and we do see that, right? We've just seen £650 million announced by the UK government in fusion. In the US, they have recently started off this milestone program. In Germany, they've just announced an uplift to over €1 billion in fusion funding. So we're seeing that, but really, I think we all have to be realistic that really to match the pace and scale of development that China can accomplish, we have to be very, very aggressive with public policy and very, very aggressive with the ability to raise money. Fundamentally, it really comes down to money as much as engineering capability. In fusion, I think actually we are much less beholden to any kind of capabilities that come out of China or other areas at the moment. But there is a real risk that could shift, particularly in some critical areas as focus shifts onto material production, and already components like power semiconductors are really critical components in fusion across several pulse power devices. So yeah, we that needs to start being factored into strategy and policy in a way that it hasn't been to date. I would say though, we still recognise that fusion is collaborative and needs to remain collaborative, and there are many very positive relationships with Chinese researchers, Chinese laboratories, and long may that continue. But geopolitics is a good thing, right? Geopolitics drives advancement, it drives competition, and I think it will be a good thing in fusion if some of that imperative to match advancement is felt.
Brilliant, thanks, Nick. I've got one last one. What does job security look like across the fusion sector, and are there any particular routes recommended for moving into it if someone were interested?
That's a fantastic question to end on, because again, this is really my personal view, but I think that having the right people, having enough of the right people in the right places is as likely to delay the deployment of fusion as any other challenge in the fusion sector right now. So job security, in my mind, looks great. I mean, I've been doing all right for the last 13 years, but no, in all seriousness, job security is in a very good place in the fusion sector at the moment. There's a real diversity of companies. If you want to work in a real startup environment, there are lots of companies raising startup amounts and working in that really sort of innovative and exciting environment that you can only find in a startup. But there are also very established companies, either established fusion companies or big engineering companies that have a strong presence in the fusion landscape, if you want to work in that kind of business environment as well, and where job security and long-term job security is good commitments from government are very strong. So we know STEP is a commitment that government are making. Government are pumping more money, £650 million into fusion. Of that £650 million, by the way, something like a percentage of that is going towards a skills development platform for fusion. So we expect, government would not be doing this if there wasn't a long-term commitment to grow this sector. So job security is in a really, really good place, and there's a real vibrancy of job roles that you can take. In terms of routes in, I don't think there's one to recommend really. Right from apprenticeships through to PhD and postdoc and everything in between, there are lots of different entry points into the sector. If you want to specialize, then PhDs is the natural and route to doing that. But you're not beholden to that. We now see apprenticeships starting at degree level apprenticeships, as well as entry level apprenticeships to come into the sector if you prefer sort of on the job training and the apprenticeship route in. So there's lots of different ways to enter the sector. Even in for those who are experienced professionals, maybe want to transfer in. If you want to know more, please email me. I'm more than happy to link anyone up to employers, possible employers, or training providers if they're keen to enter the sector. I'm very passionate on this point, and that's a wonderful way to end. So thank you very much for asking that question. If you're interested, please do come and work in fusion. There's so much interesting stuff, and you learn so much doing fusion. There's so many transferable skills that you get out of fusion that you can then take off and develop your own companies or go and do work in other sectors. It's just a really vibrant place to work.
Great, that's fantastic, Nick. Thanks for all of that, and thank you for the great questions that were asked as well. It's just past 1 o'clock now, so we'll draw this to a close. But yeah, again, thanks, Nick. So that was excellent.
Thank you, Pete, and thank you, IMechE, and everyone who joined in for inviting me. I really appreciate it. Thank you.